Close your eyes for a moment. Imagine the universe. You probably picture something like what you have seen in documentaries. A vast expanse of darkness, studded with galaxies. Space stretching infinitely in all directions. No boundaries, no edges, just endless three-dimensional space extending forever. This is how most people visualize the cosmos. This is what textbooks show. This is the default mental image even professional astronomers carry in their heads most of the time. It feels intuitively correct. Space goes on and on. If you traveled far enough in one direction, you would never wrap around and come back. You would just keep going forever, into new regions of space, filled with more galaxies, more stars, more emptiness. Infinite space. Simple, intuitive, obvious. Except it might be completely wrong. What if the universe is not infinite? What if space does not extend endlessly, but instead wraps around and connects back to itself? What if you could travel in a straight line for billions of light years and eventually arrive back where you started, having circumnavigated the entire universe? Not because you traveled in a circle through three-dimensional space, but because space itself is curved and connected in ways that make finite volume behave like it has no boundaries. This is not science fiction. This is not wild speculation. This is a genuine possibility that cosmologists have been quietly investigating for decades. And the most bizarre version of this idea suggests the universe might be tied in a literal knot, a topological knot in the fabric of space-time itself. The concept sounds absurd. How can space be knotted? Knots require rope or string, something physical that can loop and weave through itself. But space is not a thing. It is just the stage where things happen, the arena where matter and energy exist. How can an arena be knotted? Yet mathematically, it is not only possible, but natural. Topology, the branch of mathematics dealing with the properties of space that remain unchanged under continuous deformations, allows for spaces with incredibly complex structures. Spaces that twist and loop and connect in ways impossible to visualize in 3 dimensions because they involve higher dimensional structures. And one of the simplest, non-trivial topologies for a 3-dimensional space is a knot, a cosmic knot. The entire universe tied in a structure so vast that we have never noticed. A structure that might explain anomalies in our cosmological observations. A structure that changes everything about how we think the cosmos is organized. This idea emerged not from wild theorizing, but from careful observation. For decades, cosmologists have measured the cosmic microwave background, the ancient light from when the universe was just 380,000 years old. This light carries detailed information about cosmic structure and history. It should be perfectly uniform in its statistical properties, showing the same patterns regardless of which direction you look or which portion of the sky you analyze. But it is not. Anomalies exist, patterns that should not be there, alignments and asymmetries that violate the assumption that space is simple and infinite. These anomalies are subtle, not glaring contradictions, but persistent features that appear across multiple independent observations and resist conventional explanations. Researchers have proposed dozens of explanations for these cosmic microwave background anomalies: instrumental errors, foreground contamination, statistical flukes, new physics in the early universe, modified gravity. Most explanations fail to account for all the anomalies simultaneously or require assumptions that seem contrived. But one explanation, proposed initially almost as a mathematical curiosity, keeps coming back. What if space has non-trivial topology? What if the universe is finite but boundless, its shape more complex than simple infinite Euclidean space? If space wraps around and connects to itself, this would create correlations in the cosmic microwave background that look exactly like some of the observed anomalies. The patterns would be natural consequences of cosmic geometry, rather than problems requiring new physics to explain. The simplest finite topology is a 3-dimensional torus, analogous to the surface of a donut, but extended into 3 dimensions. Imagine a cube where opposite faces are identified. Exit through the right face and you re-enter through the left face. Exit through the top and you re-enter through the bottom. This makes finite space behave as if it has no boundaries. You can travel infinitely far, but the space itself is finite, a 3 torus, as mathematicians call it. This topology has been seriously considered. Observations constrain how small the universe could be if it has toroidal topology. If the universe is a torus, it must be larger than a certain size, or we would have detected the wrapping effects. Current constraints push the minimum size to scales larger than the observable universe, meaning we cannot definitively rule out toroidal topology, but also cannot confirm it. But a torus is just one possibility. Topology offers far richer structures. 3-dimensional spaces can have genus, meaning multiple holes or handles like a surface with many donut holes. They can be non-orientable like a Klein bottle, where inside and outside connect in bizarre ways. They can have twists and chirality, handedness built into the structure, and they can be knotted. A 3-dimensional space where travelling along certain paths takes you on a journey that loops through itself in a knotted pattern. This is where things get truly strange. A knotted universe is not just finite. It is finite in a way that includes intrinsic complexity. The knot is not an object in space, but a property of space itself. The cosmic fabric, tied in a configuration that mathematically resembles a trefoil knot or a more complex knot structure, existing at scales comparable to or larger than the observable universe. Why would the universe be knotted? What physical process could create such topology? The answer might lie in the universe's birth. During cosmic inflation, the first fraction of a second after the Big Bang, space expanded exponentially. If space had non-trivial topology before inflation, that topology would be stretched to enormous scales, but preserved. Inflation cannot change topology, only expand it. If quantum fluctuations during the earliest moments created topological defects, or if the universe formed with knotted structure for reasons we do not yet understand, inflation would have expanded that structure to cosmic scales. We would inherit a knotted universe, not because anything happened after the Big Bang to tie space in a knot, but because space was born knotted. Detecting cosmic topology is extraordinarily difficult. If the knotting scale is larger than the observable universe, we see only a small portion of the structure and cannot recognize it as knotted. But if the scale is comparable to the observable universe, subtle signatures appear. Correlations in the cosmic microwave background across opposite sides of the sky. Multiple images of the same distant objects seen in different directions because light has traveled different paths through the knotted space. Patterns in galaxy distributions that repeat in specific ways, reflecting the underlying topology. These signatures are detectable in principle. Whether they exist in the data we have collected is controversial. Some researchers claim to see hints, others find nothing convincing. The debate continues. What is clear is that we have no definitive proof that space is simply connected and infinite, as we usually assume. That assumption is convenient. It simplifies mathematics and matches our intuitions. But convenience and intuition are not evidence. The universe owes us no obligation to be simple. If space is knotted, if the cosmos has a shape far more complex than the infinite featureless expanse we imagine, that would be one of the most profound discoveries in the history of science. It would mean the universe is not just bigger than we thought, in the sense of containing more stuff. It would be topologically bigger, having structure and complexity at the largest possible scales. Structure that wraps around and through itself in ways our 3-dimensional minds can barely grasp. A cosmic knot binding everything into a finite but boundless whole. And we would have been living inside it all along, never suspecting that the space around us, the emptiness between galaxies, The vacuum between stars was not simple nothingness, but a knotted tapestry of geometry more intricate than we ever imagined. Infinity is a convenient assumption. It simplifies cosmology enormously. If space extends infinitely in all directions, you do not need to worry about boundary conditions. What happens at the edge of space? Nothing, because there is no edge. What is beyond the universe? Nothing, because there is no beyond. Infinity solves these problems by making them meaningless. Every cosmological equation becomes easier to write down and solve when you assume infinite space. You can use Fourier transforms freely. You can ignore global topology. You can treat space as flat Euclidean geometry extended indefinitely. Nearly every cosmology paper written in the past century makes this assumption implicitly or explicitly. Lambda CDM, the standard cosmological model, assumes space is infinite unless otherwise stated, but assuming infinity creates its own problems. Philosophical problems, certainly. What does it mean for space to be actually infinite, rather than just very large? Can physical reality encompass true infinity, or is infinity only a mathematical abstraction? These questions troubled Einstein and continue to trouble philosophers of physics. But there are also practical observational problems with assuming infinite space. Infinity predicts certain things about what we should observe, and sometimes observations do not match those predictions. The cosmic microwave background should be statistically isotropic if space is infinite and uniform. This means the temperature fluctuations should have the same statistical properties in every direction. Measure the fluctuations in one hemisphere of the sky, measure them in the opposite hemisphere. The statistics should match, not the specific pattern, those are random, but the average strength of fluctuations, the correlations between different angular scales. All the statistical measures should be identical in every direction. This is what infinite uniform space predicts. This is not what we observe. Multiple anomalies appear in cosmic microwave background data. The quadrupole and octupole, describing temperature patterns on the largest angular scales, align with each other in ways that should be extremely unlikely if the patterns were random. They also align with the ecliptic plane of our solar system, which should have absolutely nothing to do with structures imprinted on light from the edge of the observable universe billions of years before the solar system existed. This is called the axis of evil, a provocative name for a deeply puzzling correlation. Extensive analysis has failed to explain it as instrumental error or foreground contamination. It appears to be a real feature of the cosmos. Then there is the hemispherical asymmetry. The cosmic microwave background in one half of the sky shows slightly larger temperature fluctuations than the opposite half, about 3 to 5% difference depending on how you measure it. Small but statistically significant. Inflation in infinite space should produce perfectly uniform fluctuations. Finding hemispheric asymmetry suggests either inflation was not uniform, creating gradients across space, or space itself is not infinite and uniform. Perhaps space has structure that creates apparent asymmetry when we observe only a portion of it. The cold spot is another anomaly. A region in the southern sky shows significantly lower temperature than surrounding areas. The temperature deficit is too large to easily explain by random fluctuations in infinite space. Various conventional explanations have been proposed. A supervoid, a large, underdense region between us and the cosmic microwave background that causes light to lose energy passing through. But detailed galaxy surveys have failed to find a void large enough to explain the temperature drop. The cold spot remains mysterious. Its size and temperature profile match theoretical predictions for a bubble universe collision or a signature of non-trivial topology. On smaller scales, other oddities appear. The power spectrum of cosmic microwave background fluctuations describes how much fluctuation power exists at different angular scales. Lambda CDM makes precise predictions for this power spectrum. Observations match predictions extremely well on most scales, but on the very largest scales, corresponding to angles greater than about 60 degrees, the observed power is lower than predicted. There is less correlation at large angles than there should be. The deficit is not overwhelming, maybe 10 to 20%, but it is consistent across multiple analyses. Why would large-scale power be suppressed? One possibility is that space is finite. If the universe is not infinitely large, but has a size comparable to or smaller than the observable universe, certain wavelength fluctuations cannot exist. Like trying to fit long wavelengths into a small box. The longest possible fluctuation wavelength is constrained by the size of space itself. This would naturally suppress power on the largest scales, creating exactly the pattern observed. Infinite space has no such constraint. Fluctuations can exist at any wavelength. Finite space limits the longest wavelengths, suppressing large-scale power. Testing whether space is finite is tricky. The most direct method is looking for multiple images of the same object. In finite space with non-trivial topology, light can travel along different paths and wrap around the universe multiple times. You might see the same galaxy in two different directions, each image representing light that took a different path through the cosmic topology to reach you. The images would show the galaxy at different ages since the light travel times differ. This is called a topological lens. Finding such multiple images would be definitive proof of finite, non-trivial topology. Searches for topological lenses have been conducted using galaxy catalogues and cosmic microwave background data. The idea is to look for matching patterns in different parts of the sky. Temperature patterns in the cosmic microwave background should repeat if space wraps around, and we are seeing the same region from different directions. Galaxy distributions should show correlations across large angular separations if we are seeing the same structures through topological identifications. So far, no convincing detections have been made, but the searches are limited by data quality and the difficulty of recognizing matching patterns when you do not know exactly what the topology is or what scale it operates on. Upper limits have been placed on how small the universe could be if it has simple topologies like a 3 torus. If space is toroidal with a certain size, we would definitely see topological effects in the cosmic microwave background. We do not, so the universe must be either infinite or finite, with a size larger than those limits. Current limits push the minimum size to scales larger than the observable universe horizon for simple topologies. This means we cannot rule out finite space. It just needs to be large enough that the wrapping effects are subtle or occur at scales we cannot yet observe. But here is the key point. These limits apply to simple topologies. A 3 torus has very specific geometric properties and creates very specific observational signatures. But topology is vastly richer than toruses. More complex topologies create different signatures that might be harder to detect. A knotted universe is one such complex topology. The constraints from toroidal searches do not necessarily apply. The knot could exist at scales where we have not yet looked or could not recognize the signatures. Infinity is a convenient assumption, but it is just an assumption. And observations are showing hints, subtle but persistent, that the assumption might be wrong. That space might be finite with complex topology, that the universe might wrap around and connect to itself in ways that create the anomalies we observe. Infinity might not be enough to explain the cosmos. We might need knots. Knots seem simple. You tie your shoes, you tie packages. Sailors tie dozens of different knots for different purposes. Knots are practical, everyday objects. But mathematically, knots are anything but simple. Knot theory is a deep branch of topology that has fascinated mathematicians for over a century. And the mathematics of knots turns out to be directly relevant to cosmology, to understanding what shapes 3-dimensional space can have. and to determining whether the universe itself might be knotted. A mathematical knot is not quite like the knots you tie with rope. In mathematics, a knot is a closed curve in three-dimensional space that does not intersect itself. Think of taking a piece of string, tying it in a knot, then fusing the ends together to create a closed loop. The resulting object is a mathematical knot. The simplest knot is the unknot, just a circle with no crossing. Then comes the trefoil knot, which crosses itself 3 times. Then the figure 8 knot with 4 crossings. The number and configuration of crossings defines the knot type. Knots with more crossings become increasingly complex. Mathematicians have catalogued thousands of distinct knot types. What makes knots interesting mathematically is that you cannot untie them through continuous deformations. You can stretch, bend and twist a knotted loop all you want. As long as you do not cut the loop or pass parts through each other, you cannot transform a trefoil into an unknot. The knottedness is a topological property, preserved under continuous transformations. This is why knots are topological objects. Their essential structure is independent of geometry. You can embed the same topological knot in space in infinitely many different geometric configurations, but the topology remains unchanged. Now extend this to 3 dimensions. Not knots in 3-dimensional space, but 3-dimensional spaces that are themselves knotted. This is where things get mind-bending. A 3-dimensional space can have topological properties analogous to knots. Not that space contains a knotted object, but that space itself is knotted in how it wraps around and connects to itself. To visualize this, you need to think in 4 dimensions, which is impossible for human intuition. But mathematically, it is perfectly well defined. Consider a 3-dimensional space that is finite and closed, like the surface of a 4-dimensional sphere, except it is the 3-dimensional hypersurface rather than a 2-dimensional surface. This is one of the simplest finite topologies. Now imagine that this 3-dimensional space has been given a twist before its ends are connected. If you travel along certain directions, you loop back to where you started, but with a twist. This twist can be configured in ways that create knotted structures in the topology of space itself. The space becomes knotted. One way to understand this is through the fundamental group, a mathematical object that describes the loops in a space and how they can be combined. In simple infinite space, all loops are trivial. You can continuously shrink any loop to a point. The fundamental group is trivial. In a 3 torus, loops that wrap around the space cannot be shrunk to a point. The fundamental group is non-trivial but simple. In a knotted space, the fundamental group has a much more complex structure, reflecting the knotting. Loops can be woven together in ways that reflect the underlying topological knot. Why would space have knotted topology? The answer might lie in quantum gravity and the universe's origin. At the Planck scale, the smallest meaningful scale in physics, at about 10 to the power of minus 35 meters, space-time might not be smooth. Quantum fluctuations could create foam-like structures where topology constantly changes. Virtual wormholes pop in and out of existence at tight. Space-time tears and reconnects. In this quantum foam, topological defects are natural. Spaces with non-trivial topology, including knotted spaces, could form. During cosmic inflation, any such topology would be stretched to enormous scales. If the universe formed with knotted topology during the Planck era, inflation would have expanded that knot to cosmic scales comparable to or larger than the observable universe today. We would inherit a universe that is fundamentally knotted, not because anything tied space in a knot after the Big Bang, but because space was born with that topology and inflation preserved it. String theory, the leading candidate for a quantum theory of gravity, allows for complex topologies. Strings and branes can wrap around compact dimensions in ways that create topology. If our 3-dimensional space is part of a higher dimensional structure, as string theory suggests, the way it is embedded in that higher dimensional space could give it knotted topology. This is speculative. String theory has not made contact with observation enough to confirm it describes reality. but it demonstrates that knotted space is not just mathematical abstraction. It is a possibility that emerges naturally from theories attempting to unify gravity and quantum mechanics. The mathematics of knotted spaces is difficult. Topology in 3 dimensions is notoriously hard. 2-dimensional surfaces are well understood. 4 dimensions and higher have powerful tools like handle decomposition and surgery theory. 3 dimensions sits awkwardly in between, lacking the simplifying features of 2 dimensions and the extra room of higher dimensions. 3-dimensional topology was only fully classified in the early 2000s after decades of work by mathematicians like Thurston and Perelman. And even with classification, specific calculations are challenging. Determining what observational signatures a knotted universe would produce requires solving equations in curved space with non-trivial topology. The cosmic microwave background temperature fluctuations depend on how photons propagate from the surface of last scattering to us. If space is knotted, photons can travel along multiple topologically distinct paths. These paths interfere quantum mechanically, creating correlations in the observed temperature map. Computing these correlations requires understanding the geodesics, the light paths, in knotted space. This is hard. Researchers use numerical simulations and approximate methods, but exact solutions are rare. Despite the difficulties, progress has been made. Theoretical templates exist for what knotted space signatures should look like. Certain patterns in the cosmic microwave background would be smoking guns for knottedness. Correlations between widely separated points arranged in specific patterns reflecting the knot structure, symmetries that are unexpected in infinite space, deviations from Gaussianity with particular forms. These templates can be compared to observations. If the patterns are found, they would be strong evidence for a knotted universe. If not found down to certain sensitivity levels, knotted topologies with specific parameters can be ruled out. The mathematics is not just abstract curiosity. It is the language needed to translate between theory and observation. Without understanding the mathematics of knotted spaces, we cannot predict what to look for in the data. Without predictions, we cannot test the idea. The mathematics bridges the gap between the speculative notion that space might be knotted and the concrete observational program to determine if it actually is. Knot theory, developed by mathematicians for its own intrinsic interest, turns out to be essential for understanding cosmic topology. This is a beautiful example of how pure mathematics finds unexpected applications in physics. The universe speaks in the language of mathematics. If it is knotted, it speaks in the language of knot theory. And we are learning to understand that language well enough to listen for its voice in the cosmic microwave background. Imagine standing in a hall of mirrors. You see reflections of yourself in every direction. Some reflections are close, others are far away, but they are all you, just seen from different angles, or afterlight has bounced through multiple mirrors. Now replace yourself with a galaxy. Replace the mirrors with the topology of space. In a universe with non-trivial topology, you could observe the same galaxy in multiple directions because light from that galaxy has traveled through space along topologically different paths. One image might show the galaxy as it appeared 1 billion years ago. Another image might show it as it appeared 2 billion years ago because the light took a longer path through the cosmic topology. This is the cosmic Hall of Mirrors effect, and finding such multiple images would be definitive proof that space has finite topology. The concept is straightforward. In infinite flat space, light travels in straight lines forever, unless deflected by gravity. Each distant galaxy appears in exactly one direction. The map of galaxies on the sky is unique. No galaxy appears twice, but in finite space with non-trivial topology, this is no longer true. Space wraps around and connects to itself. Light can travel along different paths, and all paths can lead from the same source to us. A single galaxy can cast multiple images on our sky, each corresponding to light that took a topologically distinct path through space. The simplest example is a 3 torus. Imagine space is a cube where opposite faces are identified. A galaxy near one face sends light in all directions. Some light travels directly to us. Other light exits through a face and re-enters through the opposite face, then travels to us. This light has wrapped around the universe once. To us, it appears to come from a different direction than the direct light. We see the same galaxy twice, in opposite directions, separated by an angle corresponding to the size of the cube. The 2 images show the galaxy at different times, separated by the light travel time for wrapping once around the universe. Searching for such multiple images has been a goal for decades. The challenge is recognizing that 2 galaxies in different parts of the sky are actually the same object, seen through different topological paths. You cannot just look for identical galaxies. Galaxies evolve. The 2 images show the galaxy at different ages. They will not look exactly the same. Their morphologies, colors, and sizes will differ. What should match are fundamental properties like the statistical distribution of structures around each galaxy. If you see galaxy A in one direction and galaxy B in another direction, and the surrounding galaxy distributions are statistically identical, that suggests A and B are the same region of space seen through topology. This statistical matching approach has been applied to galaxy surveys. Researchers look for repeated patterns in the positions of galaxies on the sky. If space has topology, certain patterns should repeat with specific angular separations determined by the topology's length scale. Automated pattern matching algorithms search for such correlations. So far, no convincing detections have been made. Either space is infinite, or the topology scale is larger than the surveys cover, or the topology is complex enough that simple pattern matching does not work. The cosmic microwave background offers another avenue. Temperature patterns on the microwave background should repeat if space is finite. You would see the same pattern of hot and cold spots in different directions because you are seeing the same region of the last scattering surface through topological identifications. Circles in the sky corresponding to where space wraps around should have matching temperature patterns. Searching for such matching circles is technically challenging, but doable. Multiple searches have been conducted using data from the WMAP and Planck satellites. Some claim marginal detections of matching circles. Others find nothing convincing after accounting for statistical uncertainties and the look elsewhere effect. One tantalizing possibility is that the cold spot in the cosmic microwave background is a topological signature, not a random fluctuation or a void-induced temperature decrement, but a place where space wraps around and we are seeing the same region through 2 different paths. The collision or overlap creates a temperature anomaly. This explanation is speculative, but it demonstrates how topological effects could manifest as apparent anomalies that resist conventional explanation. If the universe is knotted rather than toroidal, finding multiple images becomes harder. A knot does not have the simple periodic structure of a torus. You cannot easily predict where matching patterns should appear. The correlations would be more complex, spread across the sky in patterns reflecting the knot structure. Detecting these would require searching for higher-order correlations, not just pairs of matching circles, but complex multi-point patterns. This is computationally intensive and statistically challenging. The larger the number of points in the pattern, the more likely you are to find apparent matches purely by chance. Distinguishing real topological correlations from random coincidences requires careful statistical analysis. Despite the challenges, the cosmic Hall of Mirrors effect remains the most direct way to detect topology. If we find multiple images of the same galaxy or matching temperature patterns in the cosmic microwave background that cannot be explained any other way, that is proof space is finite and has non-trivial topology. The absence of detected multiple images constrains how small or how simple the topology can be. But absence of detection is not proof of infinite space. Complex topologies like knots might produce subtle correlations we have not yet recognized. Future surveys will push deeper. The Vera Rubin Observatory will catalogue billions of galaxies with precise positions and properties. Machine learning algorithms will search for matching patterns at scales and complexities beyond what manual searches can achieve. The Simons Observatory and CMBS-4 will map the cosmic microwave background with sensitivity limited only by fundamental astrophysical noise. If matching circles or other topological correlations exist at detectable levels, these surveys should find them. Within the next decade, we will either confirm that space is infinite down to much smaller scales than currently constrained, or we will detect the cosmic hall of mirrors and know definitively that we live in a finite universe where the same galaxies and structures can appear in multiple places on our sky, reflections in the topological mirrors of knotted space. Space does not have to be knotted. The default assumption, the simplest possibility, is that space is infinite and topologically trivial. So why would nature choose the more complex option? What physical processes could give space non-trivial topology? And specifically, why would space be knotted rather than having some other finite topology, like a torus? These questions take us to the frontier where cosmology meets quantum gravity, where our understanding is incomplete, but tantalizing hints exist about how topology might emerge from the universe's earliest moments. Start with quantum foam. This is the idea that at the Planck scale, space-time is not smooth, but seething with quantum fluctuations. Virtual black holes and wormholes pop in and out of existence. Space-time tears and reconnects constantly. Topology changes at every point. This is predicted by attempts to quantize gravity, though we lack a complete theory to describe it precisely. If space-time is quantum foam at the Planck scale, then topology is dynamic and fluctuating. During the earliest moments of the universe, when the entire observable cosmos was smaller than the Planck length, the topology could have been anything. Pure quantum randomness. Cosmic inflation then froze whatever topology existed. Inflation stretches space exponentially. It amplifies structures from tiny to enormous, but it cannot change topology. Topology is preserved under smooth deformations like expansion. If space had knotted topology during the Planck era, inflation would expand that knot to cosmic scales. The quantum fluctuation that created the knot would be stretched until it was larger than the observable universe. We would inherit that topology as a relic from the earliest moments, frozen into the structure of space itself. This is analogous to how inflation explains the large-scale uniformity of the universe. Quantum fluctuations during inflation get stretched to cosmic scales and become the density variations that seeded galaxy formation. Topology works the same way. Topological fluctuations get stretched and frozen. The difference is that topology is global. It affects the entire structure of space, not just local density. A knotted topology means the entire observable universe, possibly even regions beyond what we can see, is knotted. The knot scale must be at least as large as the observable universe, or we would have detected its effects more obviously. Why knots specifically? One possibility is that knots are stable topological defects. In quantum field theory, defects can form when a system undergoes a phase transition. As the universe cooled after the Big Bang, it underwent several phase transitions: the electroweak transition, the QCD transition. Each transition could have created topological defects. Cosmic strings are one example. Linear defects, where field values wrap around in a non-trivial way. Monopolies are point defects. Textures are defects involving higher dimensional field configurations. Knotted space could be a global topological defect created during a phase transition in the earliest moments. String theory offers another perspective. In string theory, space-time has extra dimensions beyond the familiar 3 spatial dimensions and 1 time dimension. These extra dimensions are compactified, curled up at scales too small to observe directly. but the way they are compactified determines the physics we observe in our three large dimensions. Different compactification geometries give different particle physics. One consequence is that our three-dimensional space might be embedded in a higher dimensional space in a non-trivial way. Imagine our three-dimensional space as a surface embedded in 4 or more dimensions. The way it is embedded could give it knotted topology. Like a knotted two-dimensional ribbon in three-dimensional space, our three-dimensional space could be knotted in four-dimensional space. We cannot directly perceive the four-dimensional structure because we are confined to the three-dimensional subspace, but the topology of that subspace reflects the embedding. If string theory is correct and our space is embedded in higher dimensions, knottedness might be a natural consequence of how that embedding occurred during the universe's formation. Loop quantum gravity, an alternative approach to quantizing gravity, also predicts complex topology. In loop quantum gravity, space is fundamentally discrete at the Planck scale. Space-time is woven from quantum threads called spin networks. The connectivity of these spin networks determines the topology of space. Different network structures create different topologies. Knotted structures emerge naturally from the mathematics of spin networks. Space might be knotted because the fundamental quantum structure from which space is built has knottedness woven into it at the Planck scale. Another possibility is that the universe is part of a multiverse with complex topology. If eternal inflation creates bubble universes, and bubbles collide or interact, the topology of our bubble might be affected by those interactions. A collision could create topological identifications, regions where space wraps around because of how bubble boundaries connected. Multiple collisions from different directions could create complex topology, including knots. This is speculative, but it shows how multiverse physics could generate non-trivial topology. Perhaps most intriguingly, some researchers have proposed that topology might not be random, but selected by physical principles we do not yet understand. Just as the cosmological constant appears to have a value that allows structure formation and life, perhaps topology is selected to have properties conducive to complexity. Knotted space might have dynamical properties that favor structure formation or allow physics to operate in ways that simple topology does not. This veers into anthropic reasoning, which many physicists find uncomfortable. But if the multiverse exists with varying topologies, we would necessarily find ourselves in a topology compatible with observers. Whether that selects for knots is unknown. What is clear is that knotted topology is not just a mathematical curiosity. Multiple approaches to quantum gravity and early universe physics suggest topological complexity is natural. The universe does not need a reason to be knotted, it needs reasons not to be. If topology is dynamical in the quantum foam, if inflation preserves whatever topology exists, if phase transitions or higher dimensional embedding create defects, then non-trivial topology, including knots, should be common. The surprise would be if space turned out to be trivially flat and infinite. That would require explaining why all the topological complexity that quantum gravity predicts somehow failed to manifest. Perhaps the universe knotted itself simply because nothing prevented it, because the laws of physics at the Planck scale allow it, because space formed in a higher dimensional structure that naturally embeds as a knot. We might live in a knotted universe, not for any deep reason, but because knottedness is what happens when quantum gravity creates space from nothing, and inflation expands that space to cosmic scales, and the resulting structure happens to have wrapped and twisted in ways that tie it in a knot. Nature did not choose knottedness. Knottedness chose itself through the random but constrained processes of quantum cosmology. And we are only now, after decades of cosmological observations and theoretical development, beginning to recognize the possibility that the shape of the universe is far stranger than we ever imagined. The cosmic microwave background has been mapped with exquisite precision. The Wilkinson Microwave Anisotropy Probe operated for 9 years. The Planck satellite followed with even better instruments, observing for over 4 years. Between them, they produced temperature maps with billions of measurements covering the entire sky. The data is public. Hundreds of research teams have analysed it using countless methods. If errors existed, if systematic effects were biasing results, someone would have found them by now. Yet anomalies persist, features in the data that should not be there if space is simple and infinite, features that resist conventional explanation but might make perfect sense if space is knotted. Start with the axis of evil. The quadrupole, representing temperature patterns at the largest angular scales on the sky, should be oriented randomly. It describes how much the temperature varies when you compare opposite hemispheres of the sky. In infinite space, with random initial conditions, the quadrupole orientation should have no preferred direction. But it does. The quadrupole points toward a specific direction in space. Even stranger, the octupole, representing the next level of angular structure, aligns with the quadrupole. These two completely independent components of the temperature pattern point in nearly the same direction. The probability of this occurring by chance is less than 1%. More disturbing, this preferred direction correlates with the ecliptic plane, the plane in which Earth orbits the Sun. The cosmic microwave background originated 13.8 billion years ago from the edge of the observable universe. Our solar system formed 9 billion years later. There is absolutely no physical mechanism that could create a correlation between ancient cosmological patterns and modern solar system geometry. Yet the correlation exists at high statistical significance. Multiple papers have confirmed it using different analysis methods. This is called the axis of evil because it seems so improbably aligned. It violates the cosmological principle that the universe should look the same in all directions. Explanations have been proposed. Maybe it is foreground contamination from our galaxy that has not been properly removed. Extensive studies of galactic emission show this cannot account for the axis of evil. Maybe it is instrumental artifacts from how the satellites scan the sky, but WMAP and Planck used completely different scanning strategies and both see the alignment. Maybe it is just a statistical fluke, something that happens rarely but is not impossible. Calculate the probability carefully, and it is low enough to be concerning, but not so low that we can definitively rule out chance. The axis of evil remains unexplained by conventional physics, but in a knotted universe, preferred directions are natural. The knot structure breaks isotropy. Space is not the same in all directions, because the topology has structure. Certain directions correspond to paths that wrap through the knot, other directions do not. If you measure the cosmic microwave background in directions aligned with the knot structure, you would see correlations and alignments reflecting that structure. The axis of evil might be pointing toward the direction in which space is knotted. The quadrupole and octupole align because they are both measuring aspects of the same underlying topological structure. The correlation with the ecliptic could be pure coincidence, or it could reflect something about our location relative to the knot structure that we do not yet understand. But the key point is that knotted topology predicts preferred directions. The axis of evil is an anomaly for infinite space, but a natural feature of knotted space. The hemispherical asymmetry provides more evidence. One half of the cosmic microwave background shows temperature fluctuations about 3 to 5% stronger than the opposite half. This should not exist in isotropic space. Inflation should create the same fluctuation amplitude everywhere. Finding asymmetry means either inflation was not uniform, which requires exotic physics, or space has structure that creates apparent asymmetry. If space is knotted, the knot structure could create regions with different observable properties. We might be located in a position where one hemisphere looks through more of the knot structure than the other, creating apparent asymmetry. The temperature fluctuations are fundamentally uniform, but topology modulates how we observe them, depending on direction. The cold spot is perhaps the most dramatic anomaly. It covers about 5 degrees on the sky, roughly 10 times the width of the full moon. Within this region, temperatures are 70 microkelvin colder than the surroundings, with some areas dropping 140 microkelvin below average. The rest of the cosmic microwave background shows fluctuations barely exceeding 18 microkelvin. The cold spot is an enormous outlier. Various conventional explanations have been tried. A supervoid along the line of sight that causes light to lose energy, but galaxy surveys found no void large enough. An unusual chance fluctuation, but the probability is only 1 to 2%, and the spot is unique. Nothing similar exists anywhere else on the sky. If it is chance, why only one? Knotted topology offers a natural explanation. The cold spot could mark a location where space wraps around through the knot. Light reaching us from that direction has travelled through topological structure that affects its temperature. Perhaps constructive or destructive interference between photons taking different topological paths creates the temperature anomaly. Perhaps the cold spot is where we are looking most directly along the axis of the knot, seeing effects that are muted in other directions. The size, shape and temperature profile of the cold spot might encode information about the knot structure. Detailed modelling would be needed to test this, but the cold spot makes sense as a topological feature in ways it does not make sense as a random fluctuation. Then there is the low large-scale power. The cosmic microwave background power spectrum describes how much temperature variation exists at different angular scales. Lambda CDM predicts a specific power spectrum based on inflation and cosmic evolution. Observations match predictions extremely well on most scales. But on the very largest scales, angles greater than 60 degrees, the observed power is lower than predicted. There is less fluctuation at large angles than there should be. The deficit is modest, maybe 15 to 20%, but it is consistent across multiple analyses and cannot be explained by measurement uncertainties. In finite space, low large-scale power is expected. The universe has a maximum size. Fluctuation wavelengths larger than the universe cannot exist. This naturally suppresses power at the largest observable scales. How much suppression depends on the topology's size and structure. Simple topologies like toruses are already constrained to be larger than the observable universe, so they cannot explain much suppression. But complex topologies like knots might create more intricate patterns of suppression, depending on how the topology affects different angular modes. The low large-scale power might be direct evidence that space is finite, with a size not much larger than what we can observe. Parity violations add another layer. The cosmic microwave background should be symmetric under parity transformations, flipping left for right, but some analyses find weak violations of parity symmetry. Certain patterns appear more strongly in one-handedness than the other. This should not happen in simple isotropic space, but knots have handedness. A trefoil knot can be left-handed or right-handed. These are topologically distinct and cannot be transformed into each other. If space is knotted, it has intrinsic chirality. This chirality could manifest as parity violations in cosmological observations. The signals are weak and controversial. Not all analyses agree, but if confirmed, parity violation would be a smoking gun for knotted topology, because almost nothing else in cosmology breaks parity symmetry. Each anomaly individually can be debated. Maybe it is systematic error, maybe it is statistical fluke, maybe it is new physics unrelated to topology, but the anomalies come as a package. They all appear in the same dataset. They all point toward violations of isotropy and simple topology. They all resist conventional explanation despite decades of effort by brilliant researchers. And they all would make sense if space is knotted. The axis of evil, hemispherical asymmetry, cold spot, low large-scale power, parity violations, each predicted or at least consistent with knotted space. This convergence of multiple independent anomalies onto one explanation is compelling. It does not prove the universe is knotted, but it suggests we should take the possibility seriously. The anomalies are not going away. They are features of the best cosmological data we have, and they might be the universe trying to tell us something profound about its shape. That space is not infinite and featureless, but finite and knotted. That the cosmos has structure at the largest possible scales. Structure we have been staring at for years in the cosmic microwave background without recognizing what we were seeing. The anomalies might be the whispers of a knotted universe, waiting for us to understand the language of topology well enough to hear what they are saying. Finding evidence for a knotted universe is one of the hardest challenges in observational cosmology. You cannot point a telescope at the knot and take its picture. The knot is not an object. It is the structure of space itself at scales comparable to or larger than the observable universe. You can only infer it through subtle correlations in observations, patterns that would not exist in infinite space but naturally arise from topology. This requires careful statistical analysis of enormous datasets and comparison against theoretical predictions for what different topologies should produce. Several approaches are being pursued. None has yet yielded definitive proof, but the methods are improving, and future observations will provide the sensitivity needed to either detect cosmic knottedness or rule it out to high confidence. The most direct method is searching for matched circles in the cosmic microwave background. If space has finite size and you are near the center of the observable volume, you might see the surface of last scattering, where the cosmic microwave background originated, repeating in different directions. Circles on the sky corresponding to where space wraps around should have matching temperature patterns. The circles would not be perfect matches. Noise and evolution would blur the correspondence, but statistical matching should be detectable. Algorithms exist to search for such circles. You calculate correlation functions between pairs of circles at all possible locations and angular separations. If significantly more correlations exist than random chance predicts, that is evidence for topology. Multiple searches have been conducted using WMAP and Planck data. Results are controversial. Some researchers claim detection of matching circles with statistical significance above 3 sigma. Others reanalyze the same data and find nothing convincing after properly accounting for how many different circle pairs were tested. This is the look elsewhere effect. If you search enough places, you will inevitably find some apparent correlations by chance. Distinguishing real signals from false positives requires careful statistical frameworks. Bayesian model comparison can help, calculating the probability that the data came from a topological model versus an infinite space model. Current analyses give inconclusive results. The data quality is not quite good enough to definitively separate signal from noise. Future cosmic microwave background experiments will help. The Simons Observatory and CMBS-4 will map temperature fluctuations with sensitivities limited only by fundamental astrophysical foregrounds. If matching circles exist at currently observable levels, these experiments will see them unambiguously. If not found, the constraints on topology will tighten dramatically. We will know that if space is finite, it must be significantly larger than the observable universe for simple topologies, or must have complex topology that does not produce matching circles. For knotted topology specifically, the signatures are more subtle. A knot does not have the periodic structure of a torus that creates obvious circle matching. Instead, knottedness might manifest as complex multi-point correlations, not just pairs of circles, but triplets, quadruplets, or higher order patterns reflecting how different parts of the last scattering surface are topologically identified. Computing predictions for what these patterns should look like requires solving physics in knotted space, which is challenging. But progress is being made. Templates exist for certain knot types. These can be used as filters, searching the data for patterns matching the templates. Machine learning is being applied to this problem. Neural networks can be trained on simulated cosmic microwave background maps from different topologies. Given real data, the network attempts to classify which topology best matches what it has learned. This approach can potentially find patterns too complex for human-designed searches. Several groups are developing such machine learning tools. Results so far are preliminary, but the technique is promising. As simulations improve and training datasets grow, machine learning might reveal topological signatures that traditional statistical methods miss. Galaxy surveys offer another detection method. In knotted space, the distribution of galaxies should show patterns reflecting the topology. Not obvious repetitions, but subtle correlations in clustering across large scales. If you measure how galaxies cluster as a function of separation, the clustering signal might show features at specific scales corresponding to topological length scales. These features would appear as bumps or wiggles in the clustering power spectrum at large scales. Detecting them requires surveying enormous volumes with high precision. The Vera Rubin Observatory will catalogue billions of galaxies over half the sky. This data will enable clustering measurements to unprecedented precision on the largest scales. If topological features exist, Rubin data should reveal them. Gravitational lensing provides yet another tool. Light from distant galaxies is bent by the gravitational field of intervening matter. In simple space, this creates predictable distortion patterns. In knotted space, the topology affects how light propagates, potentially creating additional lensing effects or modifying the expected patterns. Measuring weak gravitational lensing across the sky and comparing to theoretical predictions for different topologies might reveal discrepancies that point toward knottedness. This is a new frontier. Researchers are only beginning to explore what topological lensing signals might look like and how to search for them. Gravitational waves offer a completely independent probe. Waves from merging black holes or neutron stars at cosmological distances travel through space following null geodesics, just like light. In knotted space, the propagation of gravitational waves would be affected by topology. If a single merger could be observed both directly and after wrapping around the universe, comparing the two signals would reveal the topology. This is highly speculative. Detecting a single merger is challenging. Detecting it twice through topological paths seems nearly impossible with current technology. But future gravitational wave observatories operating at different frequencies might make such observations feasible. The Laser Interferometer Space Antenna, planned for the 2030s, will detect low-frequency gravitational waves from supermassive black hole mergers across the observable universe. If space is knotted at scales LISA can probe, signatures might appear in the arrival times or polarization patterns of these waves. Combining multiple probes is essential. No single observation will definitively prove knottedness, but if cosmic microwave background anomalies, galaxy clustering features, gravitational lensing patterns, and gravitational wave signatures all consistently point toward the same topological model, the cumulative evidence would be compelling. This is how cosmology makes progress. Multiple independent observations constraining the same underlying reality. When they agree, confidence grows. When they disagree, something is wrong with our understanding. For knotted topology, we are entering the era where sufficient data exists to seriously test the idea. Within the next decade, observations will either support or rule out knottedness at various scales and for various knot types. We will not know everything, but we will know far more than we do now. And if evidence for knottedness emerges, it will be one of the most profound discoveries in the history of astronomy. proof that the universe has a shape more complex than anyone imagined. That space is not infinite, but wrapped up in a cosmic knot, binding everything into a finite yet boundless whole. What would it mean for us if the universe really is knotted? How would it change our understanding of reality, our place in the cosmos, our view of existence itself? At first glance, it might seem like an abstract mathematical detail. Whether space is infinite or knotted does not change our daily experience. The sun still rises, gravity still pulls, physics operates the same way locally, regardless of global topology. But the implications are profound, touching on some of the deepest questions humans have asked about the nature of the cosmos. First, it would mean the universe is finite, not just the observable universe, which is finite by definition because light has only had finite time to reach us, but the entire universe, all of space, everything that exists would fit within a finite volume. This seems counterintuitive. How can space have a size? What is beyond the edge? But topology resolves this paradox. Finite space with non-trivial topology has no edge. Walk in one direction long enough and you return to your starting point. Not because you circled back, but because space wraps around. You never reach an edge because edges do not exist in finite topological spaces. The universe can be both finite in volume and unbounded. No edge, no outside, just a closed structure that loops back on itself. The finiteness would have philosophical implications. Many cosmologists find infinite space unsettling. Does physical reality really contain actual infinities? Or are infinities only mathematical abstractions that approximate but never truly describe nature? A finite universe is conceptually cleaner. Everything that exists, all the matter and energy and space, fits within a definable volume. The universe is a complete object, not an endless expanse. This appeals to those who believe physics should deal with concrete finitudes rather than abstract infinities. But finite does not mean small. If space is knotted, the knot scale must be at least comparable to the observable universe, or we would have detected it already. The universe could be finite, but still unimaginably vast. Perhaps twice the size of the observable universe, perhaps 10 times larger, perhaps 1,000 times. All we know is there must be a size, a characteristic length, beyond which space wraps around. Travelling that distance in any allowed direction would bring you back to where you started. The universe would be like the surface of a sphere, but in 3 dimensions. Finite area on the sphere, no edges, travel far enough and you circumnavigate it. Second implication, there is only so much stuff. In infinite space, every possible configuration of matter exists somewhere. Every arrangement of atoms that can occur does occur infinitely, many times across the infinite expanse. There are infinitely many planets like Earth, with people identical to you living identical lives. This is the consequence of infinity, combined with finite possibilities. It leads to strange conclusions about identity, uniqueness, and meaning. But in finite space, there is only so much volume, only so many atoms, only so many planets and stars and galaxies. Each configuration is unique, or at least much rarer than in infinite space. You might truly be unique, the only version of you that exists. This restores a sense of cosmic significance that infinity strips away. Third implication, the universe has structure at the largest scales. Not just the clustering of galaxies into filaments and walls, but topology woven into the fabric of space itself. This structure is primordial, imprinted during the universe's first moments, and stretched by inflation to cosmic scales. It is unchanging, permanent. A feature of reality as fundamental as the 3 dimensions of space, or the 1 dimension of time. If space is knotted, that knottedness is part of what the universe is, not an accident or a detail, but an essential aspect of cosmic architecture. This raises questions about why. Why would the universe have knotted topology? What determined the specific knot? If space is knotted like a trefoil rather than a figure 8 or some more complex knot, why that choice? These might be unanswerable questions. Perhaps topology is random, fixed by quantum fluctuations during the Planck era. Or perhaps deeper principles we do not yet understand determine topology. Maybe topology is selected by physical laws operating at energy scales we cannot access. Maybe it is constrained by requirements for consistency of quantum gravity. Maybe if the multiverse exists, different bubble universes have different topologies, and we observe ours because it is compatible with observers. These are open questions at the frontier of theoretical cosmology. Fourth implication: we could map the entire universe, not just the observable parts, but the whole thing. If space is finite and knotted, light eventually travels all the way around. We could observe every part of space by waiting for light to circumnavigate the topology. Not in practice. The light travel time might exceed the age of the universe. But in principle, a complete map of the finite universe is possible. In infinite space, mapping everything is impossible by definition. We can only ever see a finite portion, but finite space is completely knowable, at least conceptually. This is a profound shift. The universe becomes comprehensible, not just in its local physics, but in its global structure. The cosmic knot, as complex as it might be, is a definite object with definite properties that can be completely characterized. Fifth implication: our cosmological measurements are influenced by topology. Everything we measure about the universe, expansion rates, structure growth, distances, all are potentially affected by how space is shaped. If we assume infinite space and the universe is actually knotted, our measurements could be systematically biased. For instance, distance measurements using standard candles assume light travels through simple space. If topology creates topological lensing effects, distances could be misestimated. Expansion rate measurements assume we are sampling a representative region of infinite space. If space is finite, and we happen to be in an unusual location relative to the topology, our measurements might not represent the global average. Every cosmological parameter could need revision once topology is properly accounted for. This is both unsettling and exciting. Unsettling because it means some of our most precise measurements might be wrong in subtle ways. Exciting because it means there is more structure to discover. Once we know the topology, we can correct for its effects and measure cosmic parameters more accurately. Understanding that space is knotted would not invalidate cosmology, but would elevate it to a more complete description of reality. We would finally be accounting for global structure that we have been ignoring by assuming trivial infinite topology. Living inside a cosmic knot means living in a finite but complex space. It means the universe has a shape, a definite structure at the largest scales. It means we might be able to map the entirety of existence rather than just the portion we can see. It means topology is a real physical feature, not just mathematical abstraction. And it means the cosmos is more intricate, more beautiful, more surprising than we imagined. We already know the universe is strange, quantum mechanics is strange, general relativity is strange, dark matter and dark energy are strange. Adding knotted topology to the list would be shocking, but not fundamentally more shocking than what we have already discovered. It would fit the pattern. Reality keeps revealing itself to be more complex than common sense suggests. A knotted universe would be the next step in that ongoing revelation, and we would be living inside it, navigating a space that wraps around itself in ways our ancestors could never have conceived, in a cosmos that is simultaneously finite and boundless, contained yet unlimited, knotted yet unbroken, a paradox resolved through topology, a mystery of shape on the grandest possible scale. Knotted topology does not exist in isolation. If space can be knotted, that fact connects to broader questions about the multiverse, eternal inflation, and the fundamental nature of reality. The universe having complex topology would be evidence supporting certain theoretical frameworks while constraining others. It would tell us something about how the cosmos came to be and what might exist beyond what we can observe. The knot in our space might be one knot among countless others, each in a different bubble universe. Or it might be unique, a special configuration that arose once and shaped everything we see. Either way, cosmic topology opens windows into physics at scales and energies we cannot otherwise access. Start with eternal inflation. This is the idea that inflation, once started, never completely stops. Quantum fluctuations cause inflation to end in some regions, creating bubble universes like ours. But in other regions, inflation continues. Those inflating regions expand exponentially and spawn more bubbles. The process never ends globally, even though it ends locally in each bubble. If eternal inflation is correct, our observable universe is one bubble in an infinite collection of bubbles separated by eternally inflating space. Each bubble can have different properties, different vacuum states, different physical constants, different particles and forces. The landscape of possibilities is vast. Topology fits naturally into this picture. Each bubble universe can have different topology. Some might be infinite, others finite with toroidal or spherical topology. Still others might be knotted. The topology of a bubble depends on conditions during its formation and the specific way inflation ended in that region. If quantum fluctuations during the earliest moments created topological structures, those structures would be preserved as bubbles formed. Our bubble inherited knotted topology because that is what quantum foam produced in our region. Other bubbles have different topologies because they form differently. This makes knotted topology testable indirectly. If we find evidence that our universe is knotted, that supports eternal inflation because it shows topology can vary. In models where only one universe exists, explaining why it is knotted rather than simple topology is difficult. But in eternal inflation, with infinite bubbles, every topology exists somewhere. We observe knotted topology because we happen to be in a knotted bubble. This is anthropic reasoning, but not circular. We can exist in various topologies. Observing a specific topology tells us something about the distribution of topologies in the multiverse. Bubble collisions are relevant here. During eternal inflation, sometimes two bubbles form close enough to collide before inflation separates them permanently. Collisions release energy and create patterns in the cosmic microwave background. Some researchers have claimed to find collision signatures in CMB data. Others are skeptical. The signals are subtle and controversial. But if collisions occur, and if our bubble has knotted topology, collisions might affect the knot. Perhaps collisions can change topology by connecting our space to another bubble's space in complex ways. Perhaps the knot itself is the result of a collision, a topological defect created where two bubbles merged. This is speculative, but it illustrates how topology connects to multiverse physics. The knot is not just a feature of our universe, but potentially evidence of interactions with other universes. If we find the knot and measure its properties precisely, we might learn about collision dynamics and the structure of the multiverse. Conversely, detecting collision signatures would constrain possible topologies. Certain knot structures might be more or less likely to form in collisions. Combining topology measurements with collision searches could reveal multiverse structure in ways neither approach alone could. String theory provides another connection. In string theory, the extra dimensions can be compactified in countless ways. Each compactification defines a different vacuum with different low-energy physics. This is the string landscape. Our universe occupies one point in this landscape, but the landscape might have structure. Regions with similar properties, families of vacua connected by transitions. Topology of our three large dimensions might correlate with how the 6 or 7 compact dimensions are configured. Perhaps certain compact geometries naturally produce knotted three-dimensional spaces. Understanding our topology would constrain which region of the string landscape we occupy. String theory also allows for more exotic possibilities. Brains, higher dimensional objects on which our 3 dimensions might be embedded. If our space is a brain wrapped around compact dimensions in a non-trivial way, the wrapping could create knotted topology. Imagine a two-dimensional surface wrapped around a donut shape in 3 dimensions. The surface is finite and closed, but has non-trivial topology from the wrapping. Similarly, our 3-dimensional space might be wrapped around higher dimensional structures in ways that create knotted topology. Detecting the knot would be evidence for brain world scenarios and would constrain how our brain is embedded. Loop quantum gravity offers yet another perspective. In this framework, space is fundamentally discrete. Space-time is woven from quantum threads. The connectivity of these threads determines topology. Complex connectivities produce complex topologies, including knots. If loop quantum gravity is correct, knotted space would be evidence that spin network structures have specific configurations. We could learn about quantum geometry by measuring cosmic topology. This is rare. Most aspects of quantum gravity operate at Planck scales, completely inaccessible to observation. But topology might be an exception, a quantum gravity effect amplified by inflation to observable scales, a window into the deep structure of space-time itself. The multiverse connection runs deeper. If topology varies across bubble universes and observers can only exist in certain topologies, then detecting our topology tells us about anthropic selection. Which topologies allow structure formation, star formation, chemistry, life? If most topologies do not, then finding ourselves in a life-permitting topology is expected but still informative. It tells us that, of all possible topologies, ours is in the special subset that works. This might constrain string theory or other fundamental theories by showing that most of the landscape is inhospitable and only specific regions produce life-compatible universes. Alternatively, if many topologies allow life, then our specific topology might be random. One knot among many possible knots, all equally capable of supporting observers. Then detecting knottedness tells us less about anthropic selection and more about the statistics of topology formation. How common are knots in the multiverse? Do quantum fluctuations favor simple or complex topologies? These are questions about multiverse structure that we could learn about by carefully measuring our own universe's shape. All of this assumes the multiverse exists. If it does not, if only one universe exists, then knotted topology is harder to explain. Why would the one universe have knotted rather than simple topology? Perhaps initial conditions just happen to be that way. Perhaps the laws of quantum gravity strongly favor knots for reasons we do not understand. Or perhaps the question is misguided. Perhaps asking why our universe is knotted is like asking why space has 3 dimensions. It just does. Some features of reality might not have deeper explanations. They are brute facts, the way things are. But if the multiverse exists, if eternal inflation or string theory landscape or quantum foam produces varied universes, then knotted topology makes sense. It is one possibility among many. We observe it because we are in a bubble with that topology, and studying it tells us about the multiverse, about topology formation, about quantum gravity, about cosmic structure at the largest scales. The knot connects to everything. It is a thread running through the deepest questions in cosmology and fundamental physics. Pull on the thread and the entire tapestry starts to reveal itself. This is why detecting cosmic topology matters so much. It is not just about the shape of our space, it is about understanding the context in which our universe exists, about whether we are alone or part of an infinite collection, about whether laws of physics are unique or vary across realities, about what reality itself is at its most fundamental level. The cosmic knot, if it exists, is a clue to all of this, a pattern in the largest observable structure that connects to the smallest unobservable realms of quantum gravity and the largest inconceivable expanses of the multiverse. Finding the knot would be finding a key, and the locks it opens lead to answers we have sought for centuries. The question of cosmic topology will not remain unsettled forever. Observational cosmology is advancing rapidly. Within the next decade, multiple new instruments will come online with capabilities far beyond anything currently operating. These will provide the data needed to either detect cosmic topology or rule it out to high confidence for a wide range of models. The era of speculation is ending. The era of definitive testing is beginning. Whether the universe is knotted or infinite, we will know, and that knowledge will reshape cosmology just as previous discoveries about cosmic expansion and the Big Bang did in earlier generations. The Simons Observatory is already under construction in Chile. This ground-based telescope will observe the cosmic microwave background with unprecedented sensitivity starting in the mid-2020s. Its primary goal is measuring gravitational lensing of the CMB to constrain neutrino masses and dark energy properties. But the data will be valuable for topology searches too. Higher sensitivity means better ability to detect subtle correlations. If matching circles or other topological signatures exist, Simons Observatory will have the statistical power to find them. Even null results will be valuable, tightening constraints on possible topologies. CMB-S4, the next generation CMB experiment, will be even more powerful. Deploying in the late 2020s across multiple sites in Antarctica and Chile, CMB-S4 will map temperature and polarization fluctuations with sensitivities approaching fundamental limits set by astrophysical foregrounds. This is the ultimate CMB experiment using current technology. After CMB-S4, improvements will come only from better foreground removal or space-based observatories. If topological signatures exist at any detectable level, CMB-S4 will see them. And if it does not, we will know that if space is finite, it must be significantly larger than the observable universe for simple topologies, or must have very complex topology that creates only subtle effects. Galaxy surveys will also advance. The Vera Rubin Observatory will begin operations soon, photographing the southern sky repeatedly for 10 years. Its legacy. Survey of space and time will catalogue billions of galaxies with precise positions and redshifts. This enormous dataset will enable clustering measurements on the largest scales with unprecedented precision. If topology creates features in galaxy clustering, Rubin will detect them. The survey will also search for multiple images of the same galaxies or galaxy clusters. If we are seeing the same structures through topological paths, Rubin's deep multi-epoch imaging should reveal the matches through careful pattern analysis. The Euclid Space Telescope is already observing. Its mission includes mapping billions of galaxies to constrain dark energy and dark matter properties. But the data will also test topology. Euclid's weak lensing measurements will reveal how matter is distributed across the universe. In knotted space, gravitational lensing patterns might show anomalies reflecting the topology. Comparing Euclid lensing maps to predictions for different topologies could reveal which model best fits the data. Combining Euclid with Rubin data will be especially powerful because they observe complementary wavelengths and use different techniques but cover overlapping regions of sky. Machine learning will play an increasing role. As datasets grow to billions of objects, traditional analysis methods become computationally prohibitive. Machine learning can find patterns in high-dimensional data that humans cannot recognize. Neural networks can be trained on simulated universes with different topologies, learning to recognize which topology best matches observed data. Bayesian networks can combine multiple observations, weighting evidence from CMB, galaxy clustering, lensing, all together to compute overall probabilities for different topological models. AI-driven science is still emerging, but will become standard for problems like topology detection, where signals are subtle and data is vast. Quantum computing might even contribute. Some topological calculations are exponentially hard for classical computers. Quantum algorithms might solve them efficiently. If we want to simulate cosmic microwave background patterns in complex knotted space and compare to observations, quantum computers could accelerate the calculations. This is speculative and far in the future, but it illustrates how multiple technological frontiers are converging on the topology problem. Gravitational wave astronomy will mature. The Laser Interferometer space antenna will launch in the 2030s. LISA will detect low-frequency waves from supermassive black hole mergers across the observable universe. If the universe is finite and not too large, LISA might detect the same merger through multiple topological paths. Comparing waveforms from the same event seen in different directions would directly measure topology. Even without such dramatic detections, LISA data on merger rates and black hole populations at different distances could constrain topology by revealing how cosmic volume scales with distance in ways that depend on whether space is finite. Combining all these observations will be essential. No single observation will prove or disprove topology definitively, but if CMB, galaxies, lensing, and gravitational waves all point toward the same topological model, the cumulative evidence will be overwhelming. This is how cosmology resolves questions. Multiple independent probes constraining the same reality. When they agree, confidence grows to near certainty. The next decade will provide that convergence. We will accumulate enough data from enough different sources that topology will be either detected or ruled out across a wide parameter space. If topology is detected, follow-up questions will drive research for decades. What is the specific topology? Is it a simple torus or something more complex like a knot? What is the size scale? How does it connect to inflation and quantum gravity? What does it tell us about the multiverse? These questions will require even more sophisticated observations and theoretical work. But they will be tractable because we will have established that topology is real. The search will shift from detection to characterization. If topology is ruled out, that also tells us something profound. It means the universe really is infinite, or at least so large that topology operates on scales far beyond observational reach. This would constrain models of quantum gravity and inflation. It would suggest that whatever processes created space did not produce topological complexity at observable scales. It would support simpler cosmological models. Not finding topology is still a discovery. Null results guide future research just as positive detections do. Either way, the future of topology research is bright. The tools exist or are being built. The theoretical framework is developed enough to make testable predictions. The observational strategies are defined. Within a decade, maybe 2 at most, we will know whether the universe is knotted. We will know its shape, and that knowledge will be as fundamental as knowing the universe is expanding or knowing the Big Bang occurred. It will change how we think about the cosmos, how we visualize the structure of reality, how we understand our place in existence. The age of speculation about cosmic topology is ending. The age of knowledge is beginning. And the universe is about to reveal whether it is tied in a knot or stretches infinitely in all directions. One of the most basic questions we can ask about reality is about to be answered. The shape of everything. We are about to learn it, and the answer, whatever it is, will be extraordinary. Stand outside on a clear night and look up at the stars. They seem scattered randomly across the blackness. Infinite points of light extending forever in all directions. This is the picture most people carry. The universe as an endless expanse, stars and galaxies stretching into infinity, without boundary or limit. It is a picture built on intuition and reinforced by generations of astronomy focused on cataloguing what we can see rather than questioning the geometry of space itself. But that picture might be wrong, profoundly wrong. The universe might not be infinite at all. It might be finite, wrapped up in a complex topology that ties it into a knot. Every galaxy we observe, every star, every atom, existing within a cosmic structure that loops back on itself in ways we cannot directly perceive, but can infer through careful observation. This is not fantasy. This is serious science pursued by serious researchers based on genuine anomalies in the best cosmological data we have. Whether it is true remains to be proven, but the possibility is real, and if confirmed, it would rank among the most important discoveries in human history. Consider what it would mean to know the shape of the universe. For millennia, we have asked about existence itself. What is reality? Where did it come from? What will become of it? These are philosophical questions that have occupied thinkers across cultures and centuries. But shape is different. Shape is concrete, measurable, definable. If the universe has a specific topological structure, if space is knotted in a particular way, that is a hard fact about reality. Not interpretation, not theory. Fact. The cosmos has a shape, and we have measured it. This would fundamentally change our relationship to the universe. Right now, we feel small in an infinite cosmos, insignificant specks on an unremarkable planet orbiting an average star in a typical galaxy among trillions of others extending forever. But in a finite knotted universe, the feeling changes. The cosmos becomes knowable, contained. We are still small, but we are part of a definite whole. The universe is not endlessly larger than us. It has a size, finite volume. Everything that exists fits within it. We are part of a complete structure, not lost in infinite space. The knot itself would be beautiful, a cosmic structure connecting all of space. Every point linked to every other point through the topology. Travel far enough in one direction, and you return to your origin, having traversed the knot. This is not travel through space, but travel with space, following the geodesics that space's curvature defines. The knot would be mathematical, yet real. An abstract pattern expressed in physical geometry. The largest structure in existence and the most fundamental shape reality has. A cosmic knot tying everything into one finite but boundless whole. Understanding the knot would require new mathematics, knot theory, topology, differential geometry, all applied to cosmic scales. This would be pure mathematics, finding its deepest application. The most abstract branches of mathematics, describing the most concrete feature of reality, the shape of everything. This is what makes science beautiful, the connection between abstract thought and physical truth, between equations and cosmos. A knotted universe would be that connection, made manifest at the largest possible scale. But even if the universe turns out to be infinite, the journey toward understanding cosmic topology will have been valuable. We will have learned that infinity is real, not just mathematical convenience. We will have constrained how the universe was born and evolved. We will have tested quantum gravity theories and multiverse models. We will have pushed observational cosmology to its limits. The tools and techniques developed for topology searches will apply to other questions. The data collected will reveal other mysteries. Science progresses through asking questions even when answers are uncertain. The topology question is worth asking regardless of the answer. What is certain is that we live in an extraordinary time. For all of human history until now, the shape of the universe was pure speculation. Philosophers could argue, but no one could know. Now, for the first time, we have the technology to actually measure cosmic topology, to determine with scientific rigor whether space is infinite or finite, simple or knotted. This capability is new. Within one human generation, within our lifetimes, we might definitively answer one of the oldest questions our species has asked. What is the shape of everything? Where does the universe end? Does it end? The answer is coming. Observations are being made right now that will constrain topology. Future observations will constrain it further. The convergence is happening. Within years, maybe a decade, we will know enough to say with confidence whether the universe is knotted or not. The uncertainty will be resolved, and whatever we learn will be profound. If knotted, we discover the cosmos has structure we never imagined. If infinite, we confirm that reality extends beyond all boundaries, forever. Either answer changes how we think about existence. We might be living inside a cosmic knot right now. The space around us, the vacuum between stars, the dark emptiness between galaxies, all might be wrapped in topological structure, connecting distant regions in ways we have not recognized. The anomalies in our observations might be whispers of that structure. The axis of evil pointing along the knot, the cold spot marking where topology loops, the low large-scale power reflecting finite size. These might not be problems with lambda CDM, but clues to cosmic geometry, signatures of the knot trying to tell us it exists. Or perhaps space is infinite after all. Perhaps the anomalies are statistical flukes or systematic errors we have not yet identified. Perhaps the universe really does extend forever in all directions, endless and unbounded. This too would be profound, confirmation that infinity is real, that the cosmos truly has no limit, that no matter how far we look or how long we travel, there is always more, always new galaxies, new stars, new worlds beyond what we can see. Infinity has its own strange beauty, its own unsettling vastness. If the universe is infinite, we are part of something incomprehensibly large that makes all human concerns vanishingly small by comparison. Either way, we are about to learn something fundamental about reality itself, about the structure of the space we inhabit, about whether existence is finite or infinite, about the shape of everything. This is science at its most profound, not measuring details or refining parameters, but answering basic questions about the nature of the cosmos. Questions that cut to the heart of what it means to exist in this universe. Questions our ancestors asked, looking at the same stars we see but could not answer with their tools. Questions we can finally answer with ours. The universe might be tied in a knot, a cosmic knot woven into the fabric of space itself. We had no idea. For centuries, we assumed space was simple, infinite, featureless, just emptiness extending forever. But topology is more complex than intuition suggests. Space can wrap around itself, connect in non-trivial ways, form structures that defy visualization but exist nonetheless. A knot binding all of reality into one finite structure. Everything that exists, every particle and force and field, contained within a topologically complex space that loops through itself in patterns only mathematics can fully describe. This might be the truth we have been missing, the hidden structure of reality waiting to be discovered, and we are on the verge of discovering it. The cosmic knot is calling to us through the data, through anomalies and patterns that do not fit simple models, through hints that space is stranger than we thought. We are learning to hear that call, to recognize what the universe is telling us about its shape, and soon, very soon, we will know for certain whether the cosmos is tied in a knot or stretches infinitely. We will know, and either answer will be extraordinary.